Hello friends, welcome to Math for Juniors. I'm Miss Marks. My assistant Snail seems seriously busy. Let's disturb him, huh? What are you doing, Snail?
Oh, Miss Marks, my grandparents and their friends visited home. They brought this for me as gift. Amazing, nah?
Aha! So, it's a new game that's not allowing you to focus on studies.
Don't say this, Miss Marks. You know, I was doing math while playing it.
Doing math in video games? By the way, which game is it?
Tetris. Have you ever heard of it? It's so fascinating. Different shapes and you have to adjust them.
Shapes? What kind of shapes?
A square box or a rectangle box, L-shape, straight line and many more.
Does this have any shape that resembles your tummy, huh?
No, Miss Marks. Talk about anything other than my tummy and its shape.
Okay, what all polygonal shapes does this have?
What are polygonal shapes? I want to know about them.
Yes, then let's learn about different types of polygons today.
I am very excited.
Okay, on that note, let's enter the world of math.
Sure, Miss Marks. Let's enter the virtual world.
The term polygon means many sides. Thus, a polygon is a plane figure with 3 or more straight edges as its sides. Let's learn more about it. A polygon is named after number of sides it contains. Thus, we call a polygon with 12 sides as 12 gun. Can you name polygon with 15 sides? Easy, 15 gun. When a polygon contains less than 10 sides, we name it combining a Greek-derived numerical prefix with the suffix gun. Therefore, polygon with 3 sides is called a trigon, which is popularly called a triangle. Here, the Greek word tri means 3. Similarly, a 4-sided polygon is called a tetragon, also known as a quadrilateral. Let's try to name an 8-sided polygon. We must know the Greek word representing 8. Here is a clue to know the Greek equivalent to 8. The major scale used in a piano is known as an octave because it has 8 notes, namely Do, Re, Mi, Fa, Sol, La, Ti, Do. Hence, an 8-sided polygon is known as an octagon. Polygons are used extensively in construction of buildings. For instance, can you identify this building shown here? This is the American military headquarters called the Pentagon. This building is named so owing to its shape. Tangram, a classic Chinese ancient puzzle, consists of 7 polygons, 5 triangles, 1 small square and a parallelogram. Put together, they can form a square and other interesting shapes like a bird, aeroplane, dog, etc.
Oh, so there is a pattern of 6 guns in a football. So that is called
Hexagon. A polygon with 6 sides is called hexagon.
Cool! My football also has math in it.
Yeah, this spherical football consists of a polygon.
Hexagon! Amazing! See? Math is there even in sports as well. I think even sports can replace.
Yeah, I understand. Anyways, let's zoom into the virtual world to know more criterias on classification of polygons. Polygons can be regular or irregular in shape. A regular polygon is the polygon all of whose sides are equal. The most common regular polygon are an equilateral triangle, a square, and a regular pentagon. Other category of polygons, that is, irregular polygons, are those whose all sides are not equal. The simplest examples of irregular polygons are a scalene triangle, a rectangle, a trapezium, etc. In many historic buildings such as churches, houses, palaces, there are ornamental floors comprising of regular polygons. Look at these floors made up of equilateral triangles, rhombus, and regular hexagons.
See, Miss Marks, this is what I made with a strip of paper.
Aha! Very nice! A pentagon. How did you make this?
Simple.
Oh, great, Snail. I'm impressed. I'll gift you something on this note.
Wow! Gift? What is that, Miss Marks? Something to eat?
Snail, I should remind you that you are on a strict dieting, okay? Here's a new movie. This talks about different shapes and architectures.
Oh, wow, Miss Marks. I wanted to watch this movie since long. And the shape of this CD is not a polygon.
You're right. A circle is not a polygon, since it's closed figure made up of curved line and not the straight lines. Aha! Snail, that reminds me that we can draw various regular polygons using a circle.
But, how, Miss Marks?
Let's check that up in the virtual world. Let's first see how we can draw a regular triangle, which is an equilateral triangle inside a circle. Consider this circle with the given center. The angle around its center measures 360 degrees. Now, since the triangle is plane figure obtained by joining 3 points that do not lie on a line. So, to get these points, divide 360 degrees into 3 equal central angles, each measuring 120 degrees. Mark the corresponding points on the circumference. Joining the adjacent points, we get the required equilateral triangle. Now let's look at the construction of a much higher order polygon, a nonagon. Which can be drawn by making each of the central angle equal to 360 degrees divided by 9, that is 40 degrees. In the similar manner, we can obtain all other regular polygons.
Oh, video games and building and what not. From food to football. Everywhere.
You can't come out of food, na Snail, huh?
That was just an example. And if you have a look, then food has shapes. Look at pizza and cup, cakes and...
And your tummy. That also has an interesting shape.
But it's not a polygon, ma'am.
Anyways, as we are discussing polygons, let me tell you about the existence of regular trigons in the space in the Do You Know section. Mathematicians doing space calculations discovered that if two bodies, such as the Sun and the Earth, are orbiting one another, there exist certain points in space where a smaller body, such as an asteroid or a space station, will remain in a stable orbit. They named these points as Lagrangian points.
You mean the Sun and the Earth also has such points?
Yes, the Sun-Earth system and also Moon-Earth system has 5 such Lagrangian points numbered from L1 to L5.
So, space stations at all these points remain in a stable orbit?
Not exactly. The Lagrange points L1, L2 and L3 are in unstable equilibrium. A satellite there is theoretically possible, but any disturbance will drive it out of equilibrium. Something like balancing a pencil on its point.
What about the remaining 2 points, L4 and L5? Do they behave differently?
Yes, you will be amazed to know that the Lagrange points L4 and L5, also known as Trojan points, constitute stable equilibrium.
Tell me more about the stability of the Trojan points.
An object placed at these points will be in a stable orbit with respect to the two celestial bodies. And for small departures from Trojan points, there will be an effective restoring force to bring a satellite back to the stable point.
This is hard to believe.
There's more. The position of these points is magical. L4 is exactly 60 degrees ahead, while L5 is exactly 60 degrees behind the Earth in its orbit. That is, joining the center of the Sun, and one of these stable Lagrangian points forms a regular trigon. Thus, there are two moving equilateral triangles in space. Astronomers have already found asteroids at these points.
This was very interesting.
Alright, it's now time to see how efficiently you have grasped these details.
Yeah, Miss Marks. Let's have a quick recap.
In this module, you have learnt a polygon is a plane figure with 3 or more edges as its sides. A polygon is named after number of sides it contains. A regular polygon has equal sides and equal angles. An irregular polygon has unequal sides.
This one video game helped me gain so much of knowledge.
Yeah, true. You enjoyed Snail, huh? Right?
Yes, Miss Marks, definitely. And I got a gift as well.
You and your movies, oh God. Anyways, Snail seems to be a bit busy. I would like to bid you adios. See you guys later in another episode of Math for Juniors. Till then, take care.
Goodbye.
Quadrilateral, parallelogram, rectangle, rhombus, square, trapezium are various kinds of quadrilateral. A general quadrilateral can be split into two triangles by drawing one of its diagonals. This triangulation helps us to find a formula of area for any general quadrilateral. Now let us take a look at the mathematical part to find out the area of a general quadrilateral. Area of quadrilateral ABCD is equal to area of triangle ABC plus area of triangle ADC is equal to 1/2 into AC into H1 plus 1/2 into AC into H2. Take half and AC common from the expression. We get 1/2 AC into H1 plus H2 is equal to 1/2 D into H1 plus H2, where D denotes the length of diagonal AC. Let's take an example. Find the area of quadrilateral PQR as shown in figure. By using the formula of quadrilateral is equal to 1/2 D into H1 plus H2 and substituting all value, we get area of quadrilateral PQRS is equal to 11 centimeter square. ABCD is a rhombus. Its diagonals are perpendicular bisector of each other. Area of rhombus ABCD is equal to area of triangle ACD plus area of triangle ABC is equal to 1/2 into AC into OD plus 1/2 into AC into OB. Take half and AC common from the expression. We get 1/2 AC into OD plus OB is equal to 1/2 AC into BD is equal to 1/2 D1 into D2. We can say that the area of rhombus is equal to half the product of its diagonals. Let us look into an example. Find the area of a rhombus whose diagonals are of lengths 10 cm and 8.2 cm. By using the formula of quadrilateral is equal to 1/2 into d1 into d2 and substituting all value, we get area of rhombus is equal to 41 cm square.
We already know that the diagonals of a rhombus bisect each other at right angles and therefore divide the rhombus into 4 congruent right triangles. Area of rhombus ABCD given on screen is equal to 4 into area of right triangle AOB is equal to 4 into 1 by 2 into AO into OB is equal to 4 into 1 by 2 into 1 by 2 AC into 1 by 2 BD is equal to 1 by 2 AC into BD. Hence, area of a rhombus is equal to 1 by 2 into product of the diagonals. We can also find the side of a rhombus when its diagonals are given. So, if D1 and D2 are the diagonals of a rhombus, then each side is equal to under root D1 square by 4 plus D2 square by 4 is equal to 1 by 2 under root D1 square plus D2 square. Let us understand this by means of an example. The diagonals of a rhombus are 8 cm and 6 cm. Find its area. Also, find the length of the side. Here D1 is equal to 8 cm, D2 is equal to 6 cm. So, area is equal to 1 by 2 into D1 into D2 is equal to 1 by 2 into 8 into 6 or 24 square centimeter equal to length of the side is equal to 1 by 2 under root D1 square plus D2 square is equal to 1 by 2 under root 8 square plus 6 square centimeter is equal to 1 by 2 under root 64 plus 36 or 1 by 2 under root 100 centimeter is equal to 1 by 2 into 10 or 5 centimeter. Let us take another example. The area of a rhombus is 96 square meter. If one of its diagonals is 16 meter, find its perimeter. Let us denote the other diagonal by d centimeter. Then 1 by 2 into 16 into d is equal to 96. Therefore, 8d is equal to 96 or d is equal to 96 by 8 or 12 centimeter. Therefore, the length of the other diagonal is 12 centimeter. Now to find the perimeter, we first find the length of a side of a rhombus. Therefore, side is equal to 1 by 2 under root d1 square plus d2 square is equal to 1 by 2 under root 16 square plus 12 square centimeter is equal to 1 by 2 under root 256 plus 144 centimeter. That is 1 by 2 under root 400 or 1 by 2 into 20 centimeter is equal to 10 centimeter. Hence, perimeter of the rhombus is 4 into 10 or 40 centimeter.
Today in this video, we will see examples based on the area of trapezium. This is Amit. He wants to make a picture of a pot which has parallel sides in the ratio 3:1. If the area and height of the pot are 108 square centimeter and 9 centimeter respectively, can you find the measurement of the length of parallel sides? So let us make image of pot in this way. We have to find the parallel sides of trapezium. The parallel sides are in the ratio of 3:1. Suppose x is the highest common factor of the values of sides AB and CD. So we can say that the measurements of AB and CD are x and 3x respectively. The area of the pot is given as 108 square centimeters. Do you remember the formula for area of trapezium? Well done. The area of trapezium is half the product of its height and sum of its parallel sides. So, let's find the sum of the parallel sides. We know that the measurements of the parallel sides are x and 3x respectively. So their sum will be 4x. Substituting the given values in the formula for the area of trapezium, gives a value of x as 6. Now, can you tell the value of parallel sides? Perfect. Substituting the value of x, we get the value of AB as 6 cm and the value of CD is 18 cm. This is what we had to find out in this question. Today, we learned to find the value of parallel sides of trapezium with the help of an example when the area of trapezium, height and the ratio of parallel sides are known to us.
Welcome to another video in the series Maths for Programmers. So far in this series we've been looking primarily at number theory algorithms. In this video though, we'll be looking at a basic geometry algorithm, how to find the area of a polygon. Any program that deals with computer graphics is bound to deal with polygons. A very good example is an online map. Buildings and parks and other man-made structures in an online map are typically represented by polygons. Here I'm highlighting just 4 of the polygons representing buildings. Another good example is three-dimensional computer games. So in a popular game like Counter-Strike, the various surfaces on display are usually approximated by polygons. Informally, a polygon is defined as a closed two-dimensional shape whose boundaries are all made of line segments. So the simplest kind of polygon is a triangle. Another slightly more complicated polygon is something like this, which has a large number of sides and with varying angles. However, both of these are classified as simple polygons because their edges do not intersect each other. An example of a non-simple polygon would be something like this. Here you can see that the edges of the polygon intersect each other at many points. In this video, we'll only be dealing with simple polygons and how to find the area of simple polygons. For any geometry algorithm, the choice of space is very important. Since polygons are two-dimensional shapes, the natural selection is to use a two-dimensional space. So we can use the simple Cartesian plane. So this plane has an x-axis and a y-axis. On this plane, let's say we had a point with x value 3 and y value 1 labeled by A. What is the best way to represent such a point in our program? A good design decision would be to use a separate data structure or a class to represent a point. So let's see how we can do that in C or C++. We can simply declare a structure point which has two member variables x and y to represent the x coordinate and the y coordinate of the point. Notice that we use doubles to store both the x and y coordinate, because typically the value of a coordinate can be any real number. To represent a point such as A in our code, we would simply declare a variable, let's say we call it A, of the type point, and then we can assign the x coordinate to 3 and the y coordinate to 1. Okay, now that we know how to store a point, let's draw a very simple triangle. So the first vertex of the triangle, we can keep it as A, which is at 3, 1. We'll then put up another vertex, we'll call it B at 2, 3. The third vertex though will be somewhat special. We'll choose it to be O, the origin of the coordinate system. So both the x and y values of this point O are 0. So what is the area of this triangle OAB? Because of the fact that one of the vertices lies on the origin, there is a very simple formula that involves the coordinate values of the other two vertices. So in this case, since O is the origin, the formula involves the vertices A and B, and this formula is as follows. It is the x coordinate of A multiplied by the y coordinate of B minus the y coordinate of A multiplied by the x coordinate of B, the whole divided by 2. The expression inside this pair of parentheses has a special meaning. In vector algebra, this expression stands for the cross product of the vectors A and B. With this in mind, now let's look at the code to calculate the area of a triangle, one of whose points is on the origin and the other 2 points will be taken in as arguments. So let us first define the cross product itself as a function. So given 2 points A and B, this function simply computes AX into BY minus AY into BX. So it computes the cross product of the vectors A and B. We can now write the function to compute the area. So given the points A and B, this computes the area of the triangle OAB. We simply take the cross product and divide it by 2. If we apply the formula for these values of A and B, so A is 3, 1 and B is 2, 3, we get 3 into 3 minus 1 into 2, the whole divided by 2, which is equal to 3.5. Now what if we were to exchange A and B? So A became the point 2, 3 and B became the point 3, 1. Of course the triangle itself does not change, but if you apply our formula, if you apply the code that we've written here, you will get the answer as minus 3.5. So we get the area having the same magnitude of 3.5, but the sign is opposite. This is because the cross product has a very interesting property. When the triangle OAB is in clockwise order, then the value of the cross product is negative. On the other hand, when the triangle OAB is in counterclockwise order, then the value of the cross product is positive. This property of the cross product function, where a negative value is returned for a clockwise triangle and a positive value is returned for a counterclockwise triangle, will be very useful to us later on. However, for now we need to fix our area method so that this return value is always positive, because a negative area does not make sense. To do that, we'll simply take the absolute value of cross product divided by 2. Here I'm using the abs function from the CMath library in C++. In order to use this function, we'll need to put a include statement. These two statements help us include the CMath library and then allow us to use all functions from the standard namespace. The standard namespace contains the abs function that we're using in our area method. Okay, now we know how to find the area of one kind of polygon. Basically, we know how to find the area of a triangle which has one of its vertices on the origin. Now let's try to extend our area algorithm a little bit and see how to find the area of a triangle where none of the vertices are on the origin. So let's say we had a triangle ABC like this with the origin inside of it. So one way in which we can solve this problem is by subtracting the value of the coordinates of A from A, B and C. Essentially what we are doing is translating this triangle so that A moves to the origin and B and C also translate appropriately. So we then get a triangle like this where A has been translated to the origin, and we can now use our previous formula on the triangle OBC to calculate its area. However, there's a more elegant way of computing the same area. Instead of translating the triangle so that A is at the origin, we can actually construct three smaller triangles inside of ABC by drawing three lines from the origin O, one to A, one to B and one to C. We get three smaller triangles, and the sum of the areas of these three triangles is equal to the area of the triangle ABC. Since each of these triangles has one vertex at the origin, we can simply apply our previous formula to calculate the area of OAB plus OBC plus OCA, and this will be our final answer. So now let's take a look at the code to calculate the area of a triangle given all 3 points A, B and C. So in this modified function, we now take 3 points as arguments, A, B as well as C, and none of them need to be at the origin. We calculate the sum of the triangle OAB, OBC as well as OCA, and then we take the absolute value of sum and divide it by 2. Okay, this algorithm seems to work well for any triangle with points ABC if the origin is inside the triangle, but what if the origin is outside the triangle? So let's say we have a triangle ABC like this. Let's see what happens. So initially we are computing the cross product of A and B, which means we are computing the area of the triangle OAB. Since OAB is counterclockwise in this case, the value will be positive, and I'll show this area in green. In the second step, we calculate the value of the cross product of B and C, which means we're calculating the area of the triangle OBC. Once again, since OBC is counterclockwise, this value will also be positive, and I'll be showing it in green. So now the total we have calculated is actually more than the area of the triangle. However, finally we calculate the cross product of C and A. Now OCA is actually in clockwise order, so the value will be negative, so I'll show this area in red. So we're subtracting the area OCA from the area that we've already calculated. Let me erase the areas where the red and green overlap, and we see that the area computed finally, the part shown in green, is exactly the area we needed. So our area function works for any kind of triangle, not just those containing the origin. Our next step will be to figure out how to extend this algorithm so that it works not just for triangles but for polygons containing any number of sides. So let's take an example of this six-sided polygon with vertices A, B, C, D, E and F, which contains the origin. An approach to finding the area of this polygon based on the approach we used for the triangle could be, let us divide this six-sided polygon into many smaller triangles such that each triangle has at least one vertex at the origin, and then we can just take the sum of the areas of all these small triangles in order to get the sum of the polygon. So we can take the triangle OAB and then the triangle OBC and then OCD and so on. If we look at all 6 of these triangles, the sum of their areas is equal to the sum of the polygon itself, and each of these triangles has one vertex at the origin. Now let's look at the code to compute the area of a polygon with an arbitrary number of sides. To start with, we'll actually need to update the signature of the method. We can no longer take individual points since the polygon can have any number of sides. Instead, we'll take in an array of points which gives us all the vertices of the polygon, and we'll also take an additional integer n as input, which gives us the number of sides in the polygon. So we'll take a variable called sum and initialize it to 0. This variable denotes the sum of the areas of the triangles which together make up our polygon. From our diagram to the right side, it is quite clear that an n-sided polygon will have n triangles inside it. So we'll run a loop n times, where each iteration of the loop should compute one of the triangles. Looking at the diagram, it's quite clear that each triangle has, of course, one vertex at the origin, and the other two vertices are consecutive vertices in the polygon. So we have OAB, OBC, OCD, and so on. This is true all the way until OEF, but for the last vertex F, we actually want to pair it with the first vertex of the polygon. So OF pairs with A to give us the triangle OFA. So inside our loop, we'll add the cross product of vertices of I with the vertex at I plus 1. We use this operator modulo n to take care of the special case for the last vertex, because we want the last vertex to pair with the 0th vertex. By taking modulo n, when I is n minus 1, I plus 1 will equal 0. Outside the loop, as before, we can simply take the absolute value of sum divided by 2 and return it. So we now have an algorithm that computes the area of a polygon with any number of sides, as long as it is almost convex and it contains the origin. Now the question for you is, do you think this algorithm will still work if we had a very concave polygon like this sitting outside the origin? Well, actually, this algorithm works fine even for concave polygons like these, but I'll let you figure out the proof to that one. In our next video of this series, we'll see how we can use the vector cross product to solve another important geometry problem: how to find if two line segments intersect. In the meanwhile, I hope you enjoyed this video. Thanks for watching.